Now we'll discuss the third assignment. The first problem, you have a current source driving a combination of resistors. You are asked to find out the power delivered by the current source. In a general situation, the current source could be either dissipating or delivering power. Here, the current source is driving just a bunch of resistors, so it has to be delivering power. We'll try to do it systematically. We'll compute the voltage like this and current like that, consistent with the passive sign convention, so that the product V times I is the power dissipated or absorbed. Okay. So now this I, we already know it is 12 milliamps because it's a current source of value 12 milliamps. And then this current goes through the combination of these resistors. The series combination of this is 5 kilo ohms and parallel combination of 1 and 5 is 5 by 6 kilo ohms. So there will be a voltage like this, which is 12 milliamps times 5 by 6 kilo ohms, which is 10 volts. So the voltage in this polarity will be minus 10. So the power absorbed will be 12 milliamps times minus 10 is minus 120 milliwatts. So the power delivered is plus 120 milliwatts. So the answer is 120. Okay. Here again there is some problem where you have to do some calculations with power or energy. First of all, this network consists only of resistors, so that means that eventually between these two terminals there is an equivalent resistance Req. And how much is that? To compute that, you are told that it absorbs 1.2 joules in 1 minute. Okay. So if 8 volts is applied across Req, 8 volt square divided by Req, this equals 1.2 joules divided by 60 seconds. This is the power. Okay. So this is the power that a 8 volt source will deliver into a resistance of Req, and it's given in the form of energy over a minute. So it's 1.2 joules by 60 seconds. Okay. So R equivalent in ohms will be 8 square times 60 divided by 1.2. Okay. And in the second case, a 20 volt source is applied to the same resistor Req. And what is this I1? You can easily see that this I1 is 20 volts divided by Req. Okay. Which, using this value of Req, you get 20 volts divided by Req, 8 square times 60 times 1.2. This will be in amperes. Okay. And if you calculate this number in milliamperes, you will get 6.25. Okay. So the answer is 6.25 milliamperes. In this case, there is a problem regarding the energy stored in a capacitor. Okay. The energy stored in capacitor T equals 4 milliseconds. Now energy stored in a capacitor when the voltage across it is Vc is half C Vc square. So if you know what the voltage across the capacitor is, you can find the energy. Okay. Now here a current source is charging a capacitor, and you calculate the voltage by the now familiar relationship. Vc is integral 0 to t I1 by C. Vc is in this polarity dt plus Vc of 0. Now this is given to be 0. The capacitor is initially discharged. Okay. So what you have to calculate is integral of this current and divide it by the capacitor. Integral meaning this area. Okay. To compute this, we have to find the area under this current, that is this part of it. Okay. Up to 4 milliseconds. Okay. And it's very easy to see that this area is nothing but 3 milliseconds times 5 milliamps or 15 microcoulombs. Okay. Vc at 4 microseconds will be 15 microcoulombs divided by 2 microfarads, which is 7.5 volts. Okay. and what we want is the energy, which is half times 2 microfarad times 7.5 volts square, which comes out to be 56.25 microjoules. Okay, so the answer is 56.25. Here is the next problem. You are required to find the energy delivered by the 5 volt source, and if you call this current Ix, the energy delivered by the 5 volt source is integral of 5 volts times Ix integrated over time from 0 to 3 microsecond, which is the specified period, and Ix is nothing but the inductor current IL minus I1. Okay, this integral here of Ix is the integral of IL minus integral of I1, of course all taken with respect to time over the same range from 0 to 3 microsecond. What is IL? There is a 5 volt fixed voltage across it, so the current increases like a ramp. If I plot IL versus time, it will increase like a ramp, and slope of that is given by 5 volts by L, which is 2 microhenry, which is 2.5 amperes per microsecond. This is in microseconds. At 3 microseconds, it would have reached 7.5 amperes. And the integral of IL over this period, which is this area, is given by half times base of 3 microseconds times height of 7.5 amperes. Okay, which is given by 11.25 amperes times microseconds. Okay, or 11.5 microcoulombs. And the integral under I1, that's this negative part cancels that, so basically we have only this triangle left with, and the area of that is half and base of 1 microsecond times height of 2 amperes, which gives you 1 ampere times microsecond, or 1 microcoulomb. Okay, now what we want, the total energy is 5 volts times 11.25 ampere microsecond minus 1 ampere microsecond is 5 volts times 10.25 microcoulomb, which is given by 51.25 microjoules. Okay, so that's the energy. Now let's go to the fifth problem. This is a network consisting entirely of voltage and current sources. This is actually quite easy. This is just to test your knowledge of Kirchhoff's law and proper calculations with passive sign convention. You are asked for the power delivered by the 6 volt source. There is this 6 volt source here. So power absorbed by the 6 volt source will be this voltage times current in that direction, and negative of that will be the power delivered. Okay, so you already know the voltage, which is 6 volts. You need to know the current in this direction. How do you find that? So now you can see this current is minus 9 amperes, and this current here, that's basically equal to current flowing this way, which is minus 11 amperes, and current flowing downwards, which is minus 10 amperes. So this is minus 21 amperes. Okay, and current flowing here is minus 7 amperes. Okay, so the whole thing, if you look at it, this current, which is the sum of these three currents, is minus 37 amperes. Okay, so the current flowing this way is 37 amperes. So the power absorbed by the 6 volt source is 6 volts times 37 amperes, which is 222 watts. You are asked for the power delivered by this, so that's the negative of this. So the answer is minus 222 watts. It's not delivering power, it is absorbing power. Question 6, similar question. You are asked to find the power delivered by the 4 milliamp current source. It's very easy. Always you just apply the passive sign convention and find the power absorbed. Negative of that is the power delivered. Okay, so here you have to see what is this voltage. Let me call it V. V times 4 milliamp will be the power absorbed. So how much will be V? First of all, this is Ix, which is 4 milliamps, and in this polarity the voltage is 2 kilo ohms times 4 milliamps, which is 8 volts. Okay, so the power absorbed in the current source is 8 volts times 4 milliamps, because we have 8 volts in this polarity and 4 milliamp flowing in that polarity. So this is 32 milliwatts, but this is the power absorbed. So the power delivered will be minus 32 milliwatts. Okay. Another problem with a current source, a control source and a capacitor. This current source will force a current into the capacitor. It will result in some Vx, and you can calculate this Vx by integrating the current and so on. But in this particular problem with these values given, you notice that you have Vx here, and this is a control source and its value is also exactly Vx. It has a gain of 1. So this voltage here is Vx minus Vx or 0. So you don't need to do any calculations at all if you realize this. So the voltage across the current source is 0. So it cannot deliver any energy or absorb any energy. Okay, so the answer is 0. In this case, you are asked to identify the elements that are passive. You are given a number of IV characteristics. What does passivity mean? I times V is more than 0, that is, it always absorbs power, okay, at any operating point of its characteristic. So in short, it means that if you plot I versus V, you should have the characteristics only in first or third quadrants. And it's very easy to see. First one doesn't obey that, the second one does, this one doesn't, this one also doesn't, because there is a little bit of it in the fourth quadrant. This one does, okay, and finally this one does. Okay, so B, E and H are the correct answers. Okay. And there is another problem with a number of resistors, and you're asked to find the power delivered by the minus 5 volt source. Okay. Now how would you go about doing it? You have to go through some bit of circuit analysis. Okay. You can use superposition or you can use any other method that you wish. Okay. And at this point, since we haven't talked about any other methods of circuit analysis, the easiest thing is to use superposition. So let's say you have only the minus 5 volt source, all these values are in kilo ohms. Can easily see that the resistance looking that way is 5 kilo ohms. So the total current going that way is minus 5 volt divided by 10 kilo ohms, which is minus 0.5 milliampere. Okay, that is due to only this particular source. Now you go through all the sources one by one. Okay, so now you have a 5 volt source here, and you can calculate it by doing the series parallel combination and so on, and you have to calculate the same current as before, which is that's the current flowing here, which is the same as the current flowing there. Okay, and what will you see? You will see that current will be actually minus 0.25 milliamperes. Okay, so that's what it comes out to be. And you can take the next one, which is the 5 milliamp current source. Again, when you have a single source with all kinds of complicated connections of resistors with series parallel combinations and current division and so on. You can find out. What you're interested in is the current over there, and that will turn out to be actually 1.25 milliamperes, it turns out. Okay. And finally we have this last source over here, which is 20 volts. I'm going to just scribble on this. We have 5, 10, 5, 10, 5, 10 in series with a 20 volt source, and these two are 10 kilo ohm resistors. Okay. And it turns out that if you do have 20 volts like this current in this direction will turn out to be minus 0.25 milliamperes. Okay. So if we sum up all these things, what do we get? Minus 0.5, minus 0.25, minus 0.25, that gives you minus 1 milliamp plus 1.25 milliamps. So the net current is 0.25 milliamp in that direction. Okay. So the power dissipated, which is minus 5 volts times minus 0.25 milliamps, that is 1.25 milliwatts. So 1.25 milliwatts of power is absorbed, okay, because in this polarity you have a minus 5 volt voltage, and in this direction you have a minus 0.25 milliamps. So the power delivered is minus 1.25 milliwatts. Okay. So the answer is minus 1.25. And this question is just about counting the number of nodes. How many nodes do we have? You are asked to consider each two terminal element as a branch, because in some cases you could consider the series combination of these two as some sort of a complex branch, but in this case we are only looking at simple elements, and every two terminal element is a branch. So how many nodes do we have? We have 1, 2, 3, 4, 5, 6, 7. Okay. So there are 7 nodes, and the number of independent KCL equations is 1 less, and the answer is 6. Okay. And the number of independent KVL equations, how do you find out? You have to actually count the number of independent loops that can be formed. If the number of branches is B and the number of nodes is n, B minus n plus 1 is the number of independent KVL equations. And n, we know, we already counted 7 nodes. Number of branches 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. So 11 minus 7 plus 1 equals 5. So the number of independent KVL equations you can write in the circuit is 5. Okay. So that brings us to the end of the third assignment. Again, hopefully you have been able to solve all of this. If not, go back and solve each problem step by step and find out exactly where you have gone wrong. Okay.